Here's a quick demo of some of the prototype G-code toolpath routing. I have a mold example here, which is about 30 inches wide, 30 inches deep, about 4 inches in height, with a recessed center and then a mound in the top. The 3-axis. This is a fairly simple mold example that we could make out of foam. So the 3-axis slices this mold into layer segments that could be cut with individual foam or large segments, and the foam blocks could be glued together. So the map height calculation is done by looking at the geometry and laying out a XY cutting pattern. And then we get 2 cutting paths. So out of 2 blocks of foam, the top would leave a small rim, and then the second tool path would cut the lower portion of the contour. So with the 3-axis, the tool tip is always pointing down. You can see in the line is a circular pattern that loops, and after each loop it advances on the other axis, and then you can kind of see the profile. The accuracy setting will determine how many steps. So I'll get rid of these and do the same for the 5-axis demo. So the 5-axis works in a similar way. It profiles the geometry in the scene and it maps it from the top, and then it will just angle the B and C axis based on the angle of the surface. So this isn't necessarily a useful cutting profile. It's just an example of some of the code that can read the model, an example profiling and gathering information about the normal of the surface. In practice, this is not a very good cutting option because the B and C don't freely rotate. So for example, the B axis rotates 0s facing down, -90 is one direction, and then 90 is another direction. It's able to, on a different G-code command, move left or right, but the C axis can't move quickly because the angle that it has to rotate to will be an arbitrary offset. So for example, if the B has to move from 25 degrees to 35 degrees, it just has to move 10 degrees. But on the C axis, if it has to move from one normal to another, it may have to rotate an arbitrary number of degrees around the C rotation. It could be 10 degrees, it could be 90 degrees, it could be 360 degrees, and then this would happen for each point on the surface of which there are thousands. So a better approach would be to angle the profiling on the surface and fix the B and C. An option would be to have the B move independently, but a starting point might be a good idea, just to angle different profiles on the mold and fix the B and C, and then move the XYZ to profile the part, and then choose a different B and C angle, and then run through the XYZ again. All right, so the reason that the effect is bouncing is because there's an error in the intersect code where it's trying to ping where the surface is. You'll see it bounce. So the lower cube is the simulated location where the profilers determined that the drill bit is to make contact with the surface, and the upper cube is the pivot point between the B and C. So the XYZ apparatus will move the machine tooltip, and then the B and C will rotate from the upper cube. And this cylinder, it's not quite located correctly, so just ignore that it's not actually correct positioned correctly. One of the things that you can see is the shape of the mold and the profile. Just wait for it to stop failing for whatever reason. The geometry doesn't like that. I'll have to fix that. So in this simulation, it moves the B and C to an arbitrary angle. So you can see when it's leaning, for the edges, it's going to angle up. It averages the angle over time so that it doesn't bounce too much. And once it gets to the mound in the center, you can see that the angle adjusts. So this in practice would actually be very, very slow because as you can see, it runs over this curved profile. The angle, you can see it's bend over this way, but this is also has to rotate. The B and the C has to, basically for each step, we'll have to rotate to an arbitrary angle around the C. So the machine can't really function in the way that this simulation is running. But it's an example of something that can be done with the mesh model and an approach, even though this would run very slowly on the actual machine. And the hop is a bug it's probably some kind of divide by zero error in the code that's detecting if we're looking at this region right here. It's trying to determine how far down the mesh is, and it's getting an error. So that's what's happening with the bump. I think the best approach to achieve a 5-axis with a simple algorithm would be the 3 by 2. So to angle the B and C at one angle, so 45 degrees as an example, and then fix the B and C in place, and then run through the X, Y, Z, and then choose a different B and C and run through the X, Y, and Z. And that's the demo for the example code. I can run through that later in person.